Hi all. This is the lecture 2 of chapter 1 on numerical linear algebra series. So in this lecture, we are going to see a very important property of numerical linear algebra called the concept of orthogonality. To be noted, since 1960s, many of the best algorithms of numerical linear algebra are based on this concept of orthogonality. So before going, let us understand what is the concept of adjoint or in a real sense, real analysis in the sense that it's called as transpose. So transpose is nothing but simply interchanging of the rows and columns of a matrix A. It means that uh, we are exchanging the rows as a column and columns as a row for creating another matrix called A transpose. If we are making an interchanges and formulating another matrix called A transpose and it is equal to A, then that matrix is said to be called as a symmetric matrix. So this is one concept. Then the second concept is an inner product. Let us take two vectors, column vectors, and if we are doing an element-wise multiplication and summing of all those element-wise multiplications, then that value is termed to be as an inner product of two column vectors x, y in m-dimensional space. To be noted, there is a called norm which will be detailing in the next video. Euclidean norm of vector x is related to this inner product of two column vectors, and it's a square root of the inner product of the two column vectors. And there is in a real case, if there is an x vector and y vector in m-dimensional n-dimensional space, then angle between the two vector cosine of the angle between these two vectors is termed by the equation 2.3. And there are some linear properties of this. If you are operating on inner product of these two vectors, it has a linear property. It means that x plus and x2 resultant vector is making an inner product with y. It can be equivalent to inner product of the first one with respect to y, inner product plus inner product of the second one component with respect to y. Similarly, the y1 plus y2. And also if we have any scalar multiplication, it can be taken out and it can be expressed with this inner product. And similarly, coming to the matrix, if we have an AB and make a transpose of that, it will be equivalent to B transpose and A transpose. Similarly, if we are making an AB inverse, it will be like B inverse times AB A inverse. Now comes to the concept of orthogonality. So what are meant by orthogonality of the vectors? Now let us say take two vectors x and y in an n-dimensional space. If the inner product is 0, it means that x and y are orthogonal. In real case, like in a geometrical sense, it means that the angle between these two vectors is a right angle to each other. So if we take a sets of vectors like x, another sets of vector y, and if we say there's two sets of vectors are orthogonal to each other, it means that if we take every element in x space and every element in y space, then they are orthogonal to each other because x and y are orthogonal and make it as 0. And another concept is if you are taking a set of vectors S and they are orthogonal to each other means if we are taking an x and y from S and x not equal to y, then in x transpose y is equal to 0. Another important concept of orthonormal means it satisfies the concept of orthogonality. In addition, that vector will have a norm equal to 1. An important theorem is if we say a set of vectors and they are orthogonal to each other, it means that they are linearly independent. So corollary of this theorem says that if we are having an m-dimensional space and if we have an m set of orthogonal vectors, it means that it forms a basis for the m-dimensional space. So later we will come. This is a very important concept that orthonormal basis or the best basis for the m-dimensional space. Then again, if we saw in the first lecture about that, what about the matrix vector multiplication, how we interpreted as a coefficient of expansion of x for representing the resultant vector b. Similarly, if matrices are having the columns, orthonormal columns like q1 to qn, where m is less than n, and we have a set where it is an m-dimensional space, then we can make it as a vector. We can define a vector r, which is equivalent to this expression in 2.6. And we also know that q1 to qn are orthonormal. Then what we say here is this R is going to be orthogonal to this q-dimensional space. This can be clearly see from the concept called if you multiply this one, then all the elements will become 0 except I is equal to j. Then once I is j is retained, then it means that it ends up with this relationship. From this relation, we can assume that this R is orthogonal to the orthonormal space spanned by that n-dimensional n set of orthogonal vectors. So any vector v in n-dimensional space can be expressed through this equation 2.7 as called n plus orthogonal complement, because R is orthogonal to q1 to q1. So this can be expressed in an n orthogonal components. So this is what it says about. And if in sense if n is equal to m, then it spans the whole dimensional space, then vector R will be a zero vector. So that is what here we are expressing. So if it is an m I is equal to 1 to m, then the whole it forms the basis for the n-dimensional space, and the coefficient expansion can be found through this inner product with the respect to particular vector 1. And the second interpretation is it's a sum of the m components. Each one is an outer product with qi transport. Is a rank 1 update, which we'll again see in the later part of the things. So this is what that projection operation is achieved by very special rank 1 matrix qi and rank 2. So unitary matrix, if every column is orthogonal to each other, then it is called as unitary or orthogonal matrices. And an important property is q transpose q is equal to I. So in the last video we saw that A inverse A is equal to I. It means if the particular matrix have the concept of orthogonality, then A inverse equal to A transpose. The same interpretations we'll be having here, that a what about the A inverse B, then it will be like a coefficient of expansion for that one particular in A transpose. Same here, it will is going to have the same interpretations, but here instead of A inverse we can have a transpose, because A inverse operations are very computationally prohibited operations. So this concept is going to help a lot in later part of the defining different algorithms like QR algorithm and finding eigenvalues. So another important property of orthogonal matrix is it preserves the inner product. What does that mean? Means if we are multiplying an orthogonal matrices with the respect to a particular vector x and y, then it doesn't changes the norm of the norm of this x y. At the same time, it also doesn't make any preserves the angle between these two vectors when you are doing an multiplications with the orthogonal matrices. So only through this what we can understand is orthogonal matrix either do a rotation or it makes a reflection in any vector m-dimensional vector space. Hopefully we will apply this concept of orthogonality what we see in this video in later part of the lecture series to define various important algorithms like QR algorithm to find eigenvalues and trying to solve least square problems in a stable way. Thank you.